Hello all and welcome to the next lecture on microwave engineering. So in the previous lecture, we have discussed the general analysis of wave propagation inside a waveguide. That is, we have determined the expressions for various field components such as Ex, Ey, Ez, Hx, Hy, Hz. Okay. So we have seen the procedure for analysis of wave propagation inside any general waveguide. Okay. So firstly, we will solve the expressions for Ez and Hz. So which are the components that are in the direction of the wave propagation, and use these terms and substitute them in the other terms like Hx, Hy, Ex, Ey and determine the transverse components. So this is the general procedure that is useful for analyzing how the wave propagates inside any waveguide. Okay. Now using this, let us do the analysis of wave propagation, okay, inside a planar waveguide. Okay. Yeah. So as we discussed, in a planar waveguide, we have the wave is propagating inside the waveguide in three different modes. Okay. There are three more possible modes, right? So what are they? They are, right, transverse electric mode, okay, transverse magnetic mode and transverse electromagnetic mode. So the EM wave or the microwave inside the waveguide can travel in, right, or can propagate in any one of these three modes. So we can have a transverse electric wave, we can have a transverse magnetic wave, and we can have a transverse electromagnetic wave. So when I get transverse electric wave, whenever the electromagnetic wave is vertically polarized. Okay, so when I have a vertical polarization for the EM wave, then the wave will be propagating in the transverse electric mode, and in this case the electric field will be only having a transverse component. That is, the longitudinal component of the electric field Ez will always be equal to 0 and Hz will not be equal to 0. Okay, so right, the transverse component of the electric field will only exist and the longitudinal component will be 0. That is why we call it as transverse electric wave. So everywhere the electric field is transverse to the direction of propagation. Similarly, whenever I use a parallel polarization or horizontal polarization, okay, for the electromagnetic wave, if the electromagnetic wave is parallelly polarized or horizontally polarized, then inside the waveguide, okay, so the mode that is propagating or the mode that is existing is transverse mode. Okay, so the wave propagates in a transverse magnetic mode. That means the magnetic field will always be transferred. So that means the longitudinal component of the magnetic field is always 0. So Hz is equal to 0 and Ez will not be 0. Okay. So Hz will always be equal to 0 and Ez will not be 0. That means the magnetic field will be perpendicular, right, or transverse to the direction of propagation at all places. That is why this kind of wave is called as transverse magnetic wave, or the mode of propagation is called as transverse magnetic mode. Okay. Next, coming to the special case of transverse magnetic mode, when the polarization is parallel polarization or horizontal polarization, and if the angle of launch of the wave is theta is equal to 90 degrees. That is, if I launch the wave in a normal incidence manner, right, in that case the wave will be, right, having both Ez is equal to 0 and Hz is equal to 0. That is, both the longitudinal components of electric field and magnetic field, both of them will be 0. So I will get, right, a transverse electromagnetic field. That is, both electric field and magnetic field at all places will be transverse to the direction of propagation. So I will get a TEM wave. Okay. So these are the possible modes, or these are the possible, right, waves that can the EM wave can exist in any of these three modes inside the parallel plane waveguide. Okay, so for each case the field components that are going to exist will be different. Okay, so therefore, right, let us do the analysis, or let us determine the wave field components inside the waveguide for each case. Okay. Right. So here I am going to use the general analysis that we did in the last lecture. Right. So if you are not familiar with the general analysis, kindly watch the previous lecture, because without that this lecture will not be useful. Okay, right. So firstly, let us do the analysis of TE wave, transverse electric wave propagation, TE wave propagation in a parallel plane waveguide. Okay, so from the general analysis we are right. Okay, so we are right taking two cases here. Okay, one is the waveguide I'm taking is the parallel plane waveguide, and the second is the mode of propagation is transverse electric mode. Okay, right. So from the right now I'm applying the general analysis concept to the two special requirements that we have taken, or the two special cases that we have taken. One, I'm doing the analysis for parallel plane waveguides. Second, I'm doing the analysis for a TE mode wave, okay, or for a TV configuration wave. Okay, right. So let us see this. Okay, yeah. So firstly, right, okay, because this is a TE configuration, so here EZ value will be equal to 0. The point one that we have to notice, the EZ value will be equal to 0 and HZ will not be 0. Okay, so this is the first thing, right? So the first point that we have to note here. Okay, the second point that we have to note is so because we have assumed a parallel plane waveguide, so the parallel plane waveguide, if I assume, okay, it is basically constructed, right, with the help of two parallel planes or two parallel plates that are placed, right, okay, along the z-axis, isn't it? So this is the z-axis. So the wave propagation is along z-axis, right? So the distance between the two plates is given by a, which is along the x-axis. So one plate is placed at x is equal to 0, another plate is placed at x is equal to a. Okay, so I'm placing the two parallel planes, right? The two parallel plates. Okay, one at x is equal to 0, that is at the origin, and another at x is equal to a. So at a distance of a from the right origin, okay, on the x-axis, right? So this is the thing. Now here, because it is a parallel plane waveguide, the parallel plates that you are taking, the parallel plates, right? We assume that the right, the length of the plates, or the right, the width of the plates, whatever you consider, the plates are of infinite extent. The length of the plates, okay, that is right, the dimension of the wave. This is the plate, for example. This is another plate. So I am assuming that right, it is a parallel plane waveguide, so we assume that this right, whatever the width of the waveguide is there, so that is assumed to be infinity. That means this plate is extending right from minus infinity to infinity. Similarly, this plate is extending right from minus infinity to infinity. So we assume that right, the length of the plates right along y-axis is infinity. Okay, so the plates are extending, okay, a length of infinite dimension along y-axis. So right, along y-axis there are no boundary conditions, okay, and the plate is extended off, it is extending towards infinity, right? So the length is extending towards infinity. So in this case, right, my right, any derivative with right, with respect to y is always equal to 0, because y is extending from minus infinity to infinity. So if I take the derivative of y with of any quantity with respect to y, because there is no boundary conditions, there are no boundaries, so we take always d by dou y is always equal to 0. Okay, right? So these are the 2 points that we have to remember. Okay, so firstly, the first point, as I said, because we are considering TE wave, transverse electric wave propagation. So for a transverse electric wave, the electric field component along the z axis, that is the longitudinal component of the electric field, is always equal to 0. So Ez is equal to 0. That is a point one. Second point is, because it is a parallel plane wave, right? Parallel plate, right? The parallel plates are placed right like this. So we are assuming that these are of infinite length. Okay. So for any general, because parallel plane waveguide in itself is a general theoretical assumption, right? So it does not exist practically. So just for giving the feel of how the wave propagates inside the waveguides, we are assuming it. Okay. So therefore, the length of the waveguides, okay, all along the y-axis, right, is infinity. So we assume that the plates are of infinite size. Okay. So right, because it is extending towards infinity on y-axis, right, there are no boundaries for this. So therefore, the differentiation with respect to y of any quantity will be 0. That is, dou by dou y is always equal to 0. Dou by dou y of something, anything, is always equal to 0. So these are the two right assumptions, that the two conclusions we get from the TE case. Okay. Now let us put these two conclusions in our general solution, in our general analysis, and let us determine right each component, okay, inside the waveguide. Okay. So here our aim is to find out all the components. What are all the components? Hx, Hy, Hz, Ex, Ey, Ez. So we don't need to find out Ez because it is already equal to 0. Let us find out all the other 5 components. Okay, right. So yeah. Now, firstly, we will start with the component along the direction of, as I told you, right. First, whenever we want to solve the expressions for field components, the first thing that I have to do is I have to evaluate the field components along the direction of propagation. Okay, so that is Ez and Hz. Already Ez is equal to 0, so we solved it. Now let us solve for Hz. Okay. Yeah. So the general wave equation. So general wave equation now will become, right, because for a TE wave, right, Ez is equal to 0. So there is no electric field component along the z-axis. Now the wave will be having only magnetic field component along z-axis. So that therefore the wave equation we can write it as del square Hz is equal to minus omega square mu epsilon Hz. Okay. So this is the general Hertz equation, right? So from this, right, del square is nothing but dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay. But just now we discussed that anything with respect to y is always equal to 0. Okay. So dou by dou y is always equal to 0. So dou square by dou y square is also equal to 0. So we get del square as only dou square by dou x square plus dou square by dou z square in this case. Okay. So for a parallel plane waveguide, okay, since right dou by dou y is equal to 0 for a parallel plane waveguide. So for a parallel plane waveguide, always right anything with respect to y will be 0. Okay. So that is the case, right? Now substituting it here, so we get dou square by dou x square of Hz plus dou square by dou z square of Hz is equal to minus gamma square mu epsilon Hz. Okay, right? So this is the equation, right? Now dou square by dou x square, right, into Hz. So assuming, right, we have taken, right, and we know that dou square by dou z square is nothing but gamma square. Okay. So let dou square by dou z square is equal to gamma square. So that implies, right, I can write this as gamma square into Hz, and let this term also be to this side. Okay. So what I get, omega square into mu epsilon into Hz is equal to 0. Okay, right? So what I am doing, I am letting, right, I am letting dou square by dou z square is equal to gamma square. So therefore I get this equation, right? Now this is nothing but dou square by dou x square into Hz plus, so I will write this equation as gamma square plus omega square mu epsilon into Hz is equal to 0. Okay, right? So in the previous lecture also we told, so we take this value gamma, right, gamma square plus omega square into mu epsilon is equal to a constant called as h square. Okay, so we take the value of this equal to a constant called as h square. So assuming this as h square, so we get the equation as dou square by dou x square plus h square into hz. Okay, is equal to 0. Okay, so this is the right expression that I get. Okay, so the equation that I get, right? Dou square by dou x square hz plus small h square into hz is equal to 0. Okay, right, clear? So what I have done, so right, for a TE wave, okay, the first thing, right, for finding out the right uh, the wave components inside the waveguide. So firstly what we have to do, we have to find out the field components along the along the longitudinal direction. So longitudinal direction, the field components are Ez and Hz. So we have to find out Ez and Hz. Already for a TE wave we know that Ez is equal to 0. So we have to find out Hz. Okay, so right, because the wave is propagating along Z, so we can represent the field as a wave, right, using the Hertz equation. So Hertz equation, del square Hz is equal to minus omega square mu epsilon into Hz. Okay, so here del square is nothing but, so dou square by dou x square plus dou square by dou y square plus dou square by dou z square. But in a parallel plane waveguide, dou by dou y is always equal to 0. Why? Because the plates are assumed to be of infinite extent. Okay, so substituting dou by dou y is equal to 0, right? We get the del square modified as like this. Now substituting it here, okay, and get it, right? We get this equation. So here what I am doing is I am assuming, right, dou square by dou z square is equal to gamma square. Okay, so assuming or replacing this, we will get something like this, and from this I get the equation like this. Now here again, gamma square plus omega square mu epsilon, right? We consider this property as a constant which is given by small h square, which we represent as small h square. So right, when I substitute, I'll get the final equation like this. Okay, right. So okay, this is the thing, right? Okay, we have derived up to this point. Right? Let us continue from this. Right. Now when I have this equation, so the equation that I got is del square, okay, hz, dou square by dou square hz by dou x square, right, plus small h square into his hz is equal to 0. Okay, right. So okay, so here, right, this is basically, right, what is this? This is basically a second order differential equation, in terms of the variables hz and x, isn't it? So it is a second order differential equation. So for any second order differential equation, we can write the general solution, right? So let us write this general solution. So the general solution for this, in terms of, I'm writing in terms, we can write the general solution in terms of e power x, right, e power j beta terms, but also we can write the terms in terms of sine and cosines. So right here I am going to write it in terms of sine and cosine terms. So I am writing hz is equal to, right, c1 into cos, okay, ax. So I am assuming a constant called as a, right? So what is this a value? Will discuss later. We have to derive it. Okay. So hz is equal to, right, c1 into cos ax plus c2 into cos c2 into sine ax. Okay, c2 into sine ax. So these are the two terms that I get. Okay, so hz is equal to c1 and c2 are constants. So the general solution, right, because this is a second order differential equation, the general solution for this will be of this form. Hz is equal to c1 into, right, cos ax plus c2 into sine ax, where c1 and c2 are constants and a is also a constant. Okay, so this is the expression for hz for my TE wave in case of a parallel plane waveguide. Okay, so understood, right? So it is clear till this now. Okay, so I get the value of hz, right? Now using this information, right, using the value, now I got ez, I got hz, right? Now I can calculate all the other terms. Okay, so let us calculate one by one. Okay, firstly let us calculate the value of ex. Okay, so right, let us calculate the transverse components. So firstly the value of ex for me, right, what is the general expression for ex? Ex is equal to minus 1 by h square into minus 1 by h square into dou by dou x of Ez minus dou by dou y of hz is equal, right? Okay, so Ex is equal to, right, sorry, just a second, small correction. So, right, Ex is equal to minus 1 by or minus gamma by h square into dou by dou x of Ez minus, right, this is j omega mu divided by h square into dou by dou y of hz. Okay, so you can verify this expression with the previous that one we derived. Okay, so it is derived in the general solution, right? So it is nothing new. Okay, so Ex is equal to minus gamma by h square into dou Ez by dou x minus j omega mu by h square into dou by dou hz by dou y. Okay, right, now let us substitute the values of Ez, hz, okay, and the remaining terms. Okay, but you can see that we know that for this case, for the TE wave in a planar waveguide, Ez is equal to 0 and dou by dou y is also equal to 0, right? Anything with respect to dou by dou y is always equal to 0. So therefore, right, this component is 0 and this component is also 0. So therefore, the final value of Ex is always equal to 0. Okay, right? So in case of a TE wave in the parallel plane waveguide, the component Ex is equal to 0. Okay, so simple. The general formula for Ex is this. Ex is equal to minus gamma by h square into dou by dou x of Ez minus j omega mu by h square into dou hz by dou y. Okay, so from this, in this equation, we are substituting the two terms. What is that? For a TE wave, always Ez is equal to 0, and for a planar waveguide, dou by dou y value is equal to 0. So what I get is, for a TE wave, Ex is equal to 0. Okay, right. So this is the first expression, right? So we got hx as 0, hx as 0. Okay, so let us write down it here. Hx is equal to 0. Okay, right. Now now let me go to the next, sorry, this is not hx, this is ex. Ex is equal to 0, sorry. Okay, let us go to the next term, which is ey. So ey is equal to, right, what is that I get for ey? Okay, minus gamma by h square into dou by dou y of Ez, okay, minus dou by dou y of Ez minus j omega mu by h square into dou by dou x of hz. Okay, so this is the general formula, right? If you remember properly, this is the, I think I'll get a plus here. Yeah, correct. Yeah, so the right, I'll get the expression like this. Okay, so all right, this is the expression for, right, the component ey. Okay, in general solution. Okay, right, now in our case, right, for the TE wave we got Ez is equal to 0 and dou by dou y is also equal to 0. So let us substitute those two. So I will get Ey is equal to minus gamma by h square into this, right, both of them fall over here. So 0 into 0 is 0 plus j omega mu by h square into dou by dou x of hz is not 0. So we will get this term. So hz is c1 into cos ax plus c2 into sin ax. Okay, so this is what I get, right? So this is equal to, right, this is equal to, so what I get, okay, so right, j omega mu by h square into, so when I differentiate these two with respect to x, we have to differentiate with respect to x. So c1 is a constant into cos ax will be a sin ax. Okay, correct, minus, so I'll get a minus. Then the next term again, so plus j omega mu by h square into, or let us do one thing. Yeah, so let us take this as common. So right, j omega mu by h square is common. So minus c1 into a into sin ax. Differentiation of cos ax is sin ax into a. Okay. Next, plus, right, c2 into differentiation of sin ax is again a cos AX. Okay, right? So I will get like this. Okay, this is the expression for EY. Right, EY is equal to j omega mu by h square into, right, minus C1 into A sin AX plus C2 into A cos AX. Okay, so this is the second component, right? It is existing, it is not equal to 0, right? EY component exists, EY component is not equal to 0, and it cannot be 0 also, because EX is 0, EY is equal to 0, EZ is equal to 0. If EY also becomes 0, and already EX is 0, EZ is also 0, right? If EY also becomes 0, there will be no component of electric field, right? That is not possible. Okay, so therefore EY exists. Okay, only EY exists, and that EY is given by this expression. Okay, clear with this? Yeah. So this is the expression for EY. Okay, so we got EY as not equal to 0, and EY is given by an expression, right? It is not equal to 0. We got some component. Okay, right. Now let us go for the other component. The next component, the third component, the transverse component is Hx. Okay. So what is the expression for Hx? Hx is equal to, right? Hx is equal to minus gamma by h square into, right? What is the expression I get? C1, right? Sorry, just a second. Yeah, minus gamma by h square into dou hz by dou x minus j omega epsilon divided by h square into dou by dou y of y. So this is the expression. Okay, so yeah, again this is a plus. Yeah, it doesn't matter. So minus gamma by h square into dou hz by dou x plus j omega epsilon by h square into dou by dou y of ey. So this is the expression for hx. Okay, right. In this, let us substitute the conditions. What are the conditions? One is sorry, this is not ey, this is ez. Sorry, excuse me. Yeah. So this is right. We have to substitute the two conditions for the TE wave. What are the two conditions? One is Ez is equal to 0. Other is d by dy is equal to 0. Okay. So let us substitute these two equations. So we get hx is equal to, right, minus gamma by h square into dou by dou x of hz exists, right? Hz exists. So this term exists, C1 cos ax plus C2 sin ax, right? Okay. Next, plus j omega epsilon by h square into ez is 0 and dou by dou y is also 0. So we write 0. Okay. So this entire term vanishes. Okay. So therefore this is equal to minus gamma by h square into, right, what is that we get from here? So here, right, the first term is, okay, so d by dx of cos ax, that is nothing but c1 into a into minus sin ax, isn't it? So that is the first term I get. Okay, next term what I get? So this is again c2 into a into cos ax. Okay, so this is what I get. So right, I can take out the minus term, right, common, and I can cancel out, or I can write it as it is. Hx is equal to minus gamma by h square into, right, c2 into a into cos ax minus c1 into a into, right, sin ax. Okay, so this is the term that I will get, right? So hx is equal to, right, minus gamma by h square into c2 into a into cos ax minus c1 into a into sin ax. Okay, so this is the, right, hx term for me. Okay, right? So hx is not equal to 0, so it is existing and it is given by this expression, right? Okay, right. So done. The third part, the third component is also done, right? Now let us go to the final component. So the final component for us is, right, hy. So hy is equal to, as per the general formula, so I will get gamma square by h square into dou hz by dou y, okay, plus j omega mu by h square into dou ez by dou x. Okay, dou ez by dou x, right? Okay, so in this case, right, So using the conditions, that is Ez is equal to 0 and dou by dou y is equal to 0. So we got two cases, right? So let us substitute that. Hy is equal to, so minus gamma square by h square into minus gamma by h square into, right, dou by dou y is 0. So this is term 0 and j omega mu by h square into this term dou by Ez is equal to 0, so that is also equal to 0. So everything becomes 0. Okay. So right, Hy component does not exist. Okay. So Hy, the component does not exist for the TE wave. Okay. So in case of a TE wave, right, in case of a transverse electric wave, so we got, right, Ez is equal to 0, right, Hz not equal to 0. So we will have three components. What are the three components? Ey, Hx and Hz. Okay, right, and we got the expressions for them, right? So okay, and the other three components, that is Ex is equal to 0, Hy is equal to 0 and Ez is equal to 0. So for this TE wave propagation, the wave is propagating along z axis. Electric field exists only along y axis. The electric field exists only along y axis. There is no component of electric field along z or along x. Okay, that is point 1. And the point 2 is magnetic field exists both along z axis and x axis. Okay, so it is not transverse, it is not completely transverse, it has both longitudinal and transverse, whereas electric field has only y component, which is transverse direction. So that is why we call this particular mode as transverse electric mode. Okay, right. So we got the expressions, right? We got the expressions for the field components Ey, Hx and Hz. Okay, so we are not done with it, right? Now let us apply the boundary conditions to this and let us determine the constants, right? We have used constants called as C1, C2 and A, right? Let us determine these values with the help of the boundary conditions. Okay, so here, right, yeah, let us do that. Okay, so with that, our derivation for the TE configuration will be completed. For our TE wave will be, right, perfectly analyzed in the waveguide. Okay, right. So our right, next thing is we need to calculate the constant C1, C2 and A, right? Okay, using the boundary conditions. Okay, right. Now if I take the rectangle, parallel plane waveguide, so it is situated like this. Okay, so we saw this diagram many times. Okay, right, now I have two parallel planes, right, two parallel planes that are right like this, and the plane is extended, okay, along the y-axis of infinite right length. That's what we discussed. Okay, so the plates are of infinite length along the y-axis. Okay, and therefore along y-axis we cannot have any boundary conditions. Okay, right, we cannot have any boundary conditions, right? Now coming to the other two directions, right, along z-axis. Okay, so along z-axis also, this is a plane, this is a plate that is extended over an infinite direction, or it is going, right, infinite direction along z-axis also. We don't know what is the end point of the waveguide. It is a theoretical waveguide. We discussed that it is a theoretical waveguide. So the parallel plate that you are taking, it is a two-dimensional plate. For example, if I have something like this, okay, so my let's say this is book, right? This book is a, okay, parallel plane waveguide, one plate. Okay, so right, okay, I am placing this parallel plane waveguide like this. Okay, so there are two dimensions. It's a two-dimensional quantity, isn't it? There is one dimension like this, there is another dimension like this. So this plate, we are assuming it as an infinite plate. That means the length of the plate is, right, infinite, and the width of the plate is also right, infinite. So there are no boundary conditions, okay, along y-axis, along z-axis. We don't know what is a boundary along z-axis. What is the length of the waveguide? We cannot say it is infinity, but we can say that we don't know the length of the, right, waveguide direction along z-axis. Okay, so therefore the only boundary that we know, or the only boundary that we have for us, the available is along x-axis. Okay, so right, Okay, we know that, right? Whenever this is a parallel plane conducting, right? It's a parallel plate. Okay, so we know that for any parallel plate, right, if I consider any parallel conducting plate, the electric field on the parallel conducting plate is always equal to 0. So the E bar, right, E bar on a conducting plate is equal to 0. Okay, this we know, right? So that means, right, my one plate I am placing it at x equal to 0, and one plate I am putting it at x equal to a. Okay, so that is at both these points, that is at x equal to 0 and x equal to a, my electric field should be 0, right? Why? Because, right, the electromagnetic wave or the electric field, right, cannot propagate or cannot be existing on a conducting plate. Okay, so therefore, right, I have two plates at x is equal to 0 and x is equal to a, and at both these points, right, at this both these places, my electric field should be 0. So therefore I get two boundary conditions. One, at x equal to 0, my E bar is equal to 0. This is one condition, right? And again the second condition is at x is equal to a, again my E bar is equal to 0. Okay, here my E bar, right, in general we have Ex, Ey, Ez, but in our case, for the TE wave, we just saw that Ex and Ez are equal to 0. So here, right, E bar means Ey. Okay, the component of Ey. So, right, in this case, the component of Ey should be equal to 0. So these are the two boundary conditions I get. Okay, from these two boundary conditions, I can derive the constant values. Okay, is this point clear now? I hope this point is clear, right? So, right, my two parallel plates that I'm considering, okay, placing, these two parallel plates are of infinite extent along y, along z. So I don't know what is the length of the waveguide. So I don't know what is the length of the waveguide. So I don't know any boundary values along z. Okay. Similarly, there are no boundaries existing on the y itself. Y lo manaku straight away there are no boundaries. Along Z, I don't know any component along Z. Okay, HZ, I don't have any boundary conditions for magnetic field. Okay, for magnetic field, I don't have any boundary conditions. So I cannot have a boundary condition for HZ. Okay, EZ is always 0, right? HZ, I don't have. Okay, so the only possibility is, right, because the electric field, we can have boundary conditions for electric field, right? Because of the conducting plates. So for a conducting plates, electric field is equal to 0. So using this, right, we can get two boundary conditions. The electric field will be 0 at both x is equal to 0 and x is equal to a. So I use this to determine the constants. Okay, yeah, let us see how we can do it. So firstly, what is the expression that we got for Ey, right? Ey is equal to, okay, we got Ey is equal to, right, minus, sorry, yeah, Ey is equal to, the expression that I got is minus gamma square. Yeah, so Ey is equal to, yeah, so Ey is equal to minus j omega mu by h square, j omega mu by h square into, right, dou hz by dou z. So when I do that, what I get is, right, we would have got, right, because hz we have got it as c1 cos ax, right, sorry, c1, uh, we have taken hz as c1 cos ax plus c2 sin ax. So from this, when I derive, right, apply the derivation, so minus a c1 into sin ax, okay, right, plus, right, a c2 into cos ax. Okay, so this is the expression for Ey, right? Correct. So this is the expression that we got for a1. Okay, right. Now let us apply the boundary conditions. Okay, so when I apply the boundary conditions, my first boundary condition, by applying the first boundary condition, the first boundary condition says that whenever x is equal to 0, Ey should be 0. Okay, so this implies that, okay, so Ey is equal to 0, so 0 is equal to j omega mu by h square into, right, minus a c1 into sin ax, sin a of 0, that is sin 0, okay, plus, A into C2 into, right, cos A of 0, that is cos 0. Okay, so we know that sine 0 is 0, so this term vanishes, right? Okay, so j omega mu by h square, okay, into, right, A C2 cos 0 is 1. So this is the thing. Okay, so this cannot be 0, therefore A C2 should be 0. That implies C2 value is equal to 0. Okay, so we get, right, the first equation, the first boundary, right, the first constant, which says that C2 is equal to 0. Okay, A cannot be 0, j omega mu by h square, these are all constant values, so this cannot be 0. Okay, so only, right, we can have C2 is equal to 0. Okay, so by using the first boundary condition says that whenever x is equal to 0, my Ey will be equal to 0. So therefore, substituting this, I'll get C2 equal to 0. Okay, right. So, okay, we got one value, one constant value. So let us substitute that in the general solution that we got. So Ey is equal to, now my Ey will become j omega mu by h square. So C2 is equal to 0. So this entire term gets cancelled. So minus A into C1 into sine AX. Okay. So this is the, right, now modified expression for Ey. Okay. Modified expression for Ey. Right. Now using this, right, let us apply the second boundary condition. What is the second boundary condition? The second boundary condition says that whenever x is equal to some small a, which is a constant, again my Ey will be equal to 0. Okay, so the second boundary condition says that whenever x is equal to a, Ey will be equal to 0. So let us substitute that here. So 0 is equal to minus j omega mu f by h square into a into c1 into sine a. Okay, right, so this is the thing. Okay, so in this, again, if c1 is equal to 0, if I write c1 is equal to 0, so entire term will go to 0. That means, right, Ey will be 0. Okay, which cannot happen, right? So if I take c1 is equal to 0, then the entire expression will become 0. Okay, so we will not have, right, anything left over, right, isn't it? So we cannot have c1 is equal to 0. This is not possible, right? If c1 is equal to 0, Ey will be equal to 0, right? Okay, that general solution itself becomes Ey equal to 0. So that means there is no possibility. That means, right here, the point we have to observe is, if c1 is equal to 0, then irrespective of x, ante x to sambandham lekunda, at all places Ey will be equal to 0, right? So if that is the case, that means Ey will be 0. There is already C2 equal to 0. If C1 is also becoming 0 at all places, then Ey will be 0 at all places, which means Ex 0, Ey 0, Ez is equal to 0. So there is no component of electric field. Does the EM wave exist? No. So we cannot have C1 is equal to 0. Okay. Similarly, we cannot have A equal to 0 and we cannot have j omega mu by h square equal to 0. Okay, so the only possibility is sine A into A becoming equal to 0. Okay, so, right, at this point, whenever, right, x is equal to A, Ey is becoming 0 because the sine AA is becoming 0. Okay, so, right, sine AA becoming 0. This implies that, right, my AA sin x is equal to 0 means AA should be a multiple of pi. Okay, should be a multiple of pi. Correct. So this implies that AA is equal to, let's say, m pi. M is a constant. Let us say m is a constant. So, right, m is a constant. So AA is equal to m pi. So which implies A is equal to m pi by A. Okay, so capital A is equal to small, right, m pi by A. Okay, so this is the second boundary condition from which we can find out the value of A. Okay, so see here again. So when x is equal to, the second boundary condition that we got is at the second conducting place also, right? First conducting plate is placed at x equal to 0. Their electric field will be 0. Similarly, whenever I have the second conducting plate which is placed at x equal to A, there also my electric field will be 0. Okay, so this happens, right? Okay, this is the second boundary condition. Now applying this, we get three possibilities. Okay, this cannot be 0. All these are constant terms which cannot be 0. So we get either C1 equal to 0 or sin AA equal to 0. Okay, right? If I take C1 equal to 0, that means it is a constant, right? It is not dependent on X. So if I consider C1 equal to 0, that means its value is 0 at all places along the waveguide. Okay, that says that Ey is equal to 0 at all places. Okay, Ey vanishes. Okay, which should not happen. Why? Because already Ex is 0, Ez is 0. Now if Ey also becomes 0, there will be no electric field and there is no EM wave. Okay, so we cannot have C1 equal to 0. There should be C1. Okay, there should be C1. So the possibility that we get is sin AA should be 0. Sin AA should be 0 means AA should be a multiple, integer multiple of pi. So therefore we get AA. If I write m as an integer, if I take m as an integer, so AA is equal to m pi. So which is equal to which implies capital A is equal to m pi by A. Okay. So from this I get, right, my condition. Okay. Right. So right. Okay. So from the first boundary condition I got C2 equal to 0. From the second boundary condition I get the value of A. So let us substitute that. So Ey is equal to minus j omega mu by h square into, right, in place of A, I write m pi by A into C1, right? Again, and sine, okay, this is again m pi by A into X, okay? So, right, this thing, okay? So, here again, m is an integer, pi is a constant, and A is the dimension. So, all these is a constant. C1 is also a constant, okay? So, right, a constant multiplied by another constant will give a constant value. There is nothing depending on X. Okay. The point I am making is there is nothing depending on X. All these values are constants. C1 is also a constant. So therefore, this yields a constant term. Okay. So we can call that constant as C. Let us consider this entire right term as a C. So I can write Ey is equal to minus j omega mu by h square into C, right, into sine of m pi by A into X. Okay, so this is, right, the expression for electric field inside the, right, waveguide. Okay, so the expression for the electric field component Ey in the, right, waveguide for the TE mode of propagation. Okay, clear with this? Yeah, I think right, understood. Okay, right. Now we got from the boundary conditions we got C2 equal to 0, right? So this C2, right, the value of C2, we can substitute that in the terms of Hz and, right, Hx. Okay, so we can get the simplified expressions for Hx and Hz also. Okay, so in general our Hz is written as, we got the expression for Hz as Hz is equal to, what is the expression that we got? Hz is equal to, right, yeah, yeah. So Hz for me is obtained as, okay, C1 into, right, C1 into sine AX, okay, C1 into sine AX plus C2 into cos AX. Sorry, we have taken it in reverse. Yeah, sorry. Okay, C1 into cos AX plus C2 into sin AX. So this is the expression that we got for right, Hz. Okay, general expression. Now in this expression, let us substitute C2 equal to 0 and A is equal to m pi by A. So writing that Hz is equal to, so C2 is 0, C1 into cos of m pi by A into X. Okay, so this is the expression for, right, Hz component, simplified expression for Hz component. Okay, right, now writing the expression for, right, the, what is the other term that we are left out with? H, right, H, y is 0, Hx. Okay, so what is the Hx term that I got? Hx is equal to, so what is the general solution, right? minus okay, so hx is equal to minus gamma by h square into, right, the expression that I got as c1 into, right, c1 into, so we have to differentiate this term, so c1 into a into sine ax, okay, minus I will get, okay, plus, right, c2 into a into, okay, cos ax, okay, so this is the expression that I get, right, for the hx. Now let us substitute, right, the values that we got. So what is the values we got? So we got c2 is equal to 0 and a is equal to m pi by a. Let us substitute that. Let us substitute that here. So hx is equal to minus gamma by h square into, so I'll get only c1, so minus minus gets cancelled, c1 into m pi by a into sine of, right, m pi by a into x. Okay, so this is the term that is left out. So this is equal to, so again we can take this as c, so c into gamma by h square into sine of m pi by a into x. So this is the simplified expression for hx. Okay, right? Okay, so okay, we got hz, we got hx, and we got ey. Ey is again equal to, just now we derived c into gamma by h square, sorry, j omega mu by h square into sine, right, m pi by a into x. So this is the expression for ey, this is the expression for hz, and this is the expression for hx. Okay, so these are the field components that exist in the parallel plane waveguide for a TE mode propagation. Okay, so in summary, just a brief summary. So as we discussed in planar waveguides, we can have three modes: TE, TM, and TEM. Okay, now we are discussing what is the wave propagation for a TE wave, okay, for a transverse electric wave. So when we will get transverse electric wave, whenever I incident a vertically polarized wave, that is a vertically polarized means Ez, okay, is equal to 0. So electric field is always perpendicular to the plane of incidence or to the direction of propagation, okay. So this kind of wave is called as vertically polarized wave, and whenever I do this, I get Ez equal to 0, which is called as a transverse electric wave. Okay, so here for a transverse electric wave, we get Ez is equal to 0. That is one condition. And then next, because I am considering a planar waveguide, the planar plates are assumed to be of infinite length. So therefore, we assume that there are no boundaries along y. Okay, it is infinitely extended. So we assume that anything derivative of y is always equal to 0. So d by dy is always equal to 0. So using this and using the general analysis, we have found out all the expressions for, right, the remaining field components. We have observed that Ez is equal to 0, Hz exists, Hx exists, Hy will be 0. Okay, in magnetic field, Hx, Hz will exist, Hy will be 0. For electric field, Ex, Ez will be 0, only Ey exists. Okay, so we have derived the expressions for this, okay, and then to derive the right constant values, we have used the boundary conditions. Here we get two boundary conditions. One is at x equal to 0, my Ey will be 0, and x equal to a, again Ey will be 0. So using these two, we got the expressions. Okay, so these are the field expressions for my transverse electric wave. Okay, so I hope you have understood how the the analysis of the TE mode propagation in a planar waveguide. Okay, so using these equations, in the next lecture we will see the characteristics of the TE waves inside a planar waveguide. Okay, so these equations give me what are the field components that are present inside the waveguide when the wave is propagating in TE mode. Okay, that's it, right? It will give us what are the field components that are present and what are their expressions. So from this, we will analyze the characteristics of the TE mode. That means we have certain parameters like cutoff frequency, right? Cutoff wavelength, velocity of propagation, right? What is the launching angle, right? What is the distance between the plates? All these things we will discuss in the next lecture.